In a high school chemistry class, you'll often learn about the nucleus and how it's made up of protons and neutrons. And you'll learn about these energy shells around it that the electrons reside in. So you'll often hear it as the first energy shell, n equals 1, and the second energy shell, n equals 2. And typically where a student in high school kind of tops off is with the discussion of electrons, a maximum of 2 in this first energy shell where n equals 1, and then you'll learn of maybe 8 electrons, and you'll sometimes see them just drawn on this circle that makes up the second shell. But I want to mention something, I guess, as we move into college chemistry, a change occurs. We keep this what's called Bohr model, where you consider the electrons as if they're planets orbiting the sun or the nucleus. We keep it in some regards, but we also move on to a newer model that came out in the 1920s involving wave functions and orbitals and s and p and d orbitals that you may have heard of that look like something like this, and maybe a clover leaf, things like that, that you may have learned also about electrons around a nucleus. But what I want to do in this first video is just focus on light, because I think often students learn that light can cause one electron to bump up to the second energy shell, or if electron drops down, light is given off, and that's great too. But we need to learn about light and electrons in the context of some science that came our way from 1900 to 1920. It's involving, I guess, this idea of quantum mechanics, or quanta chunk. So this first video is going to focus in on the light. I guess we'll draw it like this little arrow, and we'll say that's a bundle of light, or a photon. So the sun, we know, of course, kicks off a lot of light. The sun, we'll consider it like a hot body that kicks off a wide variety of wavelengths. Thankfully, some. I was just outside in the Kansas sun, and I was hot because some of that visible light gets through, and the visible light tends to fall near the maximum for the emission of different wavelengths by the sun. So that's good. We need it. And we don't want a lot of X-ray light that's got a very, very low wavelength. We don't want an intense amount of that hurts us, or UV A, B, or C. We don't want that either. And thankfully, the sun not only doesn't generate that much, we also have filtering of that high energy light. We say high energy. We all know that X-rays are high energy. But why? Why are they inherently high energy? That actually wasn't something commonly understood in 1900. It was thought, according to the equations they had at that time, that light can have any possible wavelength, theoretically. It wasn't inherently tied to an energy. So as they took their equations, wave mechanics and Maxwell's equations, and tried to theoretically come up with an equation for the distributions of wavelengths and their intensities, it didn't match experimental here in black. They had what was called the UV catastrophe, where the equations, again, developed from theory, could not be made to fit the experimental curve that was known. That was a problem. In the 1900s, not a minion, but Maxwell, he had a mustache and some glasses, he came up with an approach where he actually just took the curve and sort of fit a mathematical expression to it, and then tried to look at it maybe and see how it might relate back to theory. Well, one of the key, principles he took was this, that with any wavelength of light, you can't just have any energy. He said that at the low wavelengths, you inherently have a low energy light. And at the very high wavelengths, let's say X-ray, inherently, by just the nature of its being, like when you shine that light, it's going to have a high energy. Even if just one photon comes out of a light bulb or some source, it's still going to have a punch to it. And here's why. Maxwell proposed this equation, that there's a constant between the frequency of light and the energy that's never broken. So if frequency, just to kind of relate the frequency to wavelength, if frequency goes up, the energy has to go up for that frequency of light to stay constant, or to stay equal to h. So if that was 10, this has to be, let's say, 20. If this goes up to 100, then that has to be 200. So there was a constant. If this goes up, that has to go up to keep this constant. Now, frequency is related to wavelength in this way. We know from C equals lambda times nu that if the wavelength goes down in value or gets smaller, the wavelength, let's say for this blue one, I'll represent this position by this little short wavelength. It has a very, very short wavelength, very low, then its frequency is very high. So according to Planck, this would be very high energy light. Even though it has a very, very short wavelength, it's not about amplitude, how much crest or trough you have, crest, trough. It's not about that. It's just about the inherent wavelength or frequency. If the wavelength is very short, it means the frequency is high, it means the energy is high. And in the opposite way, if we're on the other end of this bell-shaped curve, red, or not red light, but just this red position, that means we have a very long wavelength. That means the frequency is very low, because if the wavelength is high, the frequency is low. If frequency is low, then that E has to come down, the energy inherent to that frequency, to keep H constant. Now what I want to close with is this, and this is just mind-blowing. I think, okay, it is something new for them at that time to understand light as having an inherent energy to it. So let's take this long wavelength and kind of put a model to it. So in the kitchen, I took a peanut and painted it, or marked it red. There's my peanut, and just really think of it as this. This peanut, if I drop it from this distance, has a certain energy. It doesn't hit very hard on this surface because there's just not much mass or momentum to it when I drop it. You need to understand that the energy then for light is in the same way, doesn't have much punch to it when I drop it. So there's my little peanut, red. He's a long wavelength light beam, or pulse of light, or photon. And it has very low amount of energy. The next one kind of coming down in wavelength, but going up in frequency. If frequency goes up, the E has to go up. So I got to be a little bit bigger because it has to have more punch. So there, I just dropped it. Now it's not as heavy as a peanut. It's just actually a green tomato. It says, oh, a particle. A photon that got bigger. It has a bigger, I don't know if it's bigger photon, but it has more energy inherent to that photon, which is the coolest thing. These pulses of light then, or we're going to say they're like a particle, it has this sort of particle-like property. It brings a certain chunk of energy. Every one of these wavelengths comes out with a certain energy. Bam. Again, according to this constant. The last one, way down here at UV and X-ray, here comes big old blue. Now I just took an onion out of the kitchen and I said, I'm going to say he's the blue position. He's the X-ray. When I drop this, that just brings bigger punch. It has more, I guess, a quanta value to it. It's bigger. Not all quanta is the same. We're not just going up incrementally. You have this bringing with one photon, it brings that much energy to it. So one photon here, not as much, and even with a peanut, even less. So there you go. There's our sort of way in which we can kind of understand light as bringing with it inherently, based on its frequency, a certain amount of punch or energy. Bye-bye.